Calculate the exact bounded area between the curves f of x equals x squared plus 16 and g of x equals x plus 72 over the closed interval from -7 to +10. When determining bounded area, it's important to graph both functions on the coordinate plane. Because if we look at our notes below, to determine the area bounded between two functions, the integrand function is f of x minus g of x, where f of x must be the top function and g of x must be the bottom function. And the limits of integration are normally determined by the points of intersection of the two functions. But in this case, we're given a specific interval, the closed interval from -7 to +10. So I've already graphed both functions on the coordinate plane. I've also graphed the line x equals -7, this vertical line, and x equals +10, this vertical line here on the right. Notice from x equals -7 to x equals +8, the linear function is on top and the quadratic function is on the bottom. However, from x equals 8 to x equals 10, the quadratic function is on the top and the linear function is on the bottom. This indicates we'll have to set up and evaluate two definite integrals to determine the total bounded area. If we weren't able to determine the points of intersection of the linear function and quadratic function, we could determine x equals -7 and x equals +8 by setting the two functions equal to each other and then solving for x. The result is a quadratic function where the solutions are x equals -7 and x equals +8. You may want to try solving that equation to confirm the x-coordinates of the points of intersection. But I'm going to go ahead and set up the definite integrals that will determine the total bounded area, which again is going to require two definite integrals. The total area is equal to, first we have the definite integral from -7 to +8, where the integrand function again is the linear function minus the quadratic function, or the quantity x plus 72 minus the quantity x squared plus 16, integrated with respect to x, and then plus the integral from 8 to 10, where the integrand function is now the quadratic function minus the linear function. And therefore the integrand function is the quantity x squared plus 16 minus the quantity x plus 72. Next, we will simplify the integrand functions and write the terms in descending order. For the first integral, we have -x squared plus x, and then 72 minus 16 is equal to 56, giving us plus 56. Plus, for the second integral, the integrand function simplifies to x squared minus x minus 56. Notice the integrand functions are opposites. And now let's determine the antiderivatives. For the first integral, we have -x cubed divided by 3, or -1/3 x cubed, plus x squared divided by 2, or plus 1/2 x squared, plus 56x. And then for the second integral, the antiderivative is the opposite. We have 1/3 x cubed minus 1/2 x squared minus 56x. And now we can determine big F of 8 minus big F of -7 plus big F of 10 minus big F of 8. So first we substitute 8 for x in the first antiderivative. And then minus big F of -7. So now we substitute -7 for x. And now looking at the second part, we need to find big F of 10 minus big F of 8. So we have plus big F of 10. We substitute 10 for x. minus big F of 8. To save some time, I've already evaluated this expression. This is equal to 928 divided by 3 minus negative 1,519 divided by 6 plus negative 830 divided by 3 minus negative 928 divided by 3, which gives us 1,125 divided by 2 for this first difference, and then plus the second difference is 98 divided by 3, and the final sum is equal to 3,571 divided by 6. And because this is the bounded area, this would be square units. So I did skip quite a few of these calculations, but hopefully you found this helpful.